Okay, our new lesson today is 2.4 measures of variation. First thing that we talk about is the range. Range of a set of data is the difference between the maximum and minimum entries. Yes, we did this to find class width already. We took the maximum entry and subtracted the minimum entry. That's all this is. Example is if you needed one. Number of times Brooklyn would have called me Quentin per class this year. So I put the lowest number at 1 and the highest number at 25. I think that would be a day where she was being real ridiculous to have done it 25 times in one class. But if she had done it 25 times on the highest day and 1 on the lowest day, then in order to find the range, we would just do 25 minus 1 to get 24. So the range of our data would be 24. That measures how spread out the data is. So this entire section is going to be talking about the spread of our data, how far spread out it is, and how it all relates to each other. The deviation of an entry X, so that would be any entry in the population data set, is the difference between that entry and the mean mu of the data set. So from the data set below, the mu equals 41.5. So I know that my average is 41.5. So then I can take the salary in thousands and find the deviation. To find the deviation, it's x. Deviation of x is x minus mu. So you could go through and you could do 41 minus 41.5. You could probably calculate all those out in your head fairly quickly. I'm going to show you how to use the stat program to do it. So you go to stat, then enter on edit, and you enter all these in L1. So 41, 38, 39, 45, 47, 41, 44, 41, 37, and 42. Okay. So, in order to find our deviation in thousands, then you would go over to L2, push up, and then you do second, and then 1 because it has the L1 above it. So that would be L1, in other words, all of list 1 minus 41.5. That's going to give us all of our deviations in thousands. So it's one real step instead of having to do these all separate. And then you can just scroll down when you need to. And there's a reason I'm writing all this down, because we're going to have to do more information based off of this. Okay. So now, if I take all of these points and add it together to find out what our deviation would be like overall, the sum of our deviations, and max it out of there, and add all this together, And when I add it all together, I get the sum of x minus mu equals 0. And that makes sense. If we found the average, then the sum of all the differences between each number and the average should basically come out to be 0. As a matter of fact, we don't always just want to know what the mean of a data set is. We want to know what the spread of the data is. Are all the numbers close together, or are they spread real far apart? The sum of the deviations is always going to be 0, because some are above it and some are below it. So if we just use the sum of the deviations, it does not show how far the data is spread out, which means we use variance to counteract this notion. The population variance of a population data set of n entries is this formula. Population variance equals sigma squared equals the sum of x minus mu squared, so squaring each one of those x minus mu's and dividing that entire sum by n. So in order to do this, we have to square each one of these deviations. So let me copy my deviations down again. Now, if you take a college stats course, the majority of them are not going to let you use a graphing calculator. You're going to be calculating all of these by hand or basically on a scientific calculator. And we're going to find out why a little later. Negative 0.5, negative 4.5, and 0.5. Okay, so then we can find x minus mu squared. We would do negative 0.5 squared, which is going to give us 0.25. Then you would do negative 3.5 squared, which gives you 12.25, and so on down the list. So we have to find each one of those. And I'll show you the easy method for that as well. You go over to L3, go up, and then push second 2, because the little yellow L2 is above that. And then you just square it. And that gives you all of your values. So just having this feature makes it a lot easier and less tedious to do it. Okay, so those are all our x minus mu's. But to find population variance, we have to take the sum of, or those are all our x minus mu squareds. To find the variance, we have to take the sum of all of those and divide it by n. Okay, so we're going to add all these together now. Now, a couple different ways to do this. First one is to enter them all in, obviously, adding each one of them. The second way is to go second list. So second stat, going to list, and then go over to math. If you go down to sum, and then push second, and it's all stored in L3, And it gives you the sum of that being 88.5. Don't trust the calculator, you can do it by hand, but I promise you it is the same. So the sum of x minus mu squared equals 88.5. Now, in order to find our population variance, we have to do that. So sigma squared equals 88.5 divided by the number of entries. So I believe it's 10. 2, 4, 6, 8, 10. Okay. So your population variance is 8.5. 8.85. My bad. So it's 8.85, right? So what's population variance tell us? Does it tell us how far each data entry is away on average? Well, if you look at it, I don't think any of them are 8.5 away. I mean, if we just look at our deviation, none of them are 8.85 away, so that really does not tell us. If you think about it, what does square thousands of dollars mean? Square thousands of dollars doesn't tell us anything. There is no such thing as this square thousands of dollars. So we have to take the square root of the variance to get what's called the standard deviation. So the population standard deviation of a population data set of n entries is the square root of the population variance. So sigma equals square root of the sum of x minus mu squared all over n. So if we take the square root of 8.85, that gives us what our standard deviation is. Which is about 2.97. So the standard deviation away from the mean is 2.97. Exciting stuff. Aren't you pumped up to go through all those steps? Even though we have the calculator to do it. So back in my day, we weren't allowed to even use the calculators, scientific calculators on it. We had to do it all by hand in our college stats class. So you guys are lucky kids. This is just a summary for how to find population variance and standard deviation. So first, find the mean of the population of the set. Find the deviation of each entry. Square each deviation. Add to get the sum of the squares. Divide by n to get the population variance. And then find the square root of the variance to get the population standard deviation. All right. Sample variance is different. So the sample variance and sample standard deviation of a sample data set of n entries are listed below. Sample variance is almost exactly the same thing. It's the sum of x minus x bar squared, all divided by, the only difference is n minus 1. So remember, x bar is your mean for a sample. So you're taking each data entry and subtracting the mean of the sample from it. Then you square those and find the sum. Then just divide by n minus 1 instead of n. So if our last entry would have been a sample instead of a population, instead of dividing by 10, we would divide by 9. Same thing with the standard deviation. Last part is just to find the square root of it all. So for sample standard deviation, you are just finding the, I don't know why this S is here at all, but you are just finding the sample variance here and then taking the square root. And then here's each step for finding sample variance and standard deviation. It's just to help you out if you forget to do it, how to do it on the test. Alright, now we get to find sample variance and standard deviation. In a study of high school football players that suffered concussions, research placed the players into two groups. Players that recovered from the concussions in 14 days or less were placed in group 1. So this would be the first group. 4, 7, 6, 7, 9, 5, 8, 10, 9, 8, 7, and 10. So that's how long it took them to recover. So first, we're going to have to go in and clear our stat out. I'm going to go edit, and I'm going to clear all three out. So you go up to L3, clear, down, over to L2, clear, down, into L1, clear, down. Now we enter all those data points in. So 4, 7, 6. Okay, and to find the deviation, well, first we have to find the mean of those. So to find the mean, you gotta enter them all in. So we get 90 when we enter them all in. Then how many data entries are there? 2, 4, 6, 8, 10, 12. So we divide by 12. So that gives you a mean of 7.5. So because this is a sample, it's an X bar equals 7.5. All right, so let's go back into stat and edit. And we can go over to L2. Got to go up where the heading is. It says L2. Then you do second, L1 minus 7.5. And then enter. Okay, it gives us our deviation. Negative 3.5, 1.5, negative 1.5, negative 0.5, 1.5, negative 2.5, 0.5, 2.5, 1.5, 0.5, All right. If we add those deviations all together, we do second quit, second list, sum, L2, you should get 0. Otherwise, you made a mistake. So it's an easy way to check and see if you're on the right path. Then we have to find the squares of all those. So we go over to L3, second, L2, squared equals all this. All right. And if you remember, we now are at the point of finding our sample variance. So we take the sum of all those, second list, math, sum of L3. We divide that by n minus 1. So s squared equals the sum of x minus x bar squared divided by n minus 1. So s squared equals 39 divided by 11. That gives you 3.5, around there. 3.545. But that's not our standard deviation yet. So you just take the square root and that gives you 1.88. So that's how we find sample variance and sample standard deviation. Now, if you haven't listened to anything to all the way up to this point, here's the time to start paying attention. If we go into stat, and I'm going to go edit L3, I'm going to clear it out. I'm going to clear L2 out. So all that we have is our beginning data. All right. So I enter my data in, and I push second, or not second stat, but just push stat again. Now we're back to where our stat screen was. Instead of editing, go over to calc. You see one var stats at the top. Push enter and enter again. Now you will see that there is X bar, which is 7.5. That was our original mean. You will see that the sum of X was 90. Sum of X squared was 714. You don't need any of that. S of X is your sample standard deviation. That is 1.88. So you could go through everything we just did, or you could push stat, enter your data in, stat again, over to calc, one var stats, enter, enter, and it will give you your sample standard deviation. What if it was a population? It gives you your population standard deviation right under that. What if I ask for population variance? You just take 1.88 and square it. Or sample variance, 1.88 squared will give you this. So it's valuable information to have. All right. I basically went through it all just so you knew how to do it by hand. But you could do this every single time for all of these. All right. Okay. Many real-life data sets have distributions that are approximately symmetrical and form a bell shape. Empirical rule shows how valuable standard deviation can be as a measure of variation. So you're going to find the more that you do statistics that the more you do it, the more you will see things come into a standard bell-shaped curve. And they call it the standard curve. It works like this. In the middle is where your mean is, and the majority of the data is going to fall within one standard deviation above and below the mean. So this is considered one standard deviation. Even though it's two columns, it's one standard deviation because it's one standard deviation this direction and one standard deviation this direction. 68% of your data is going to fall within one standard deviation of the mean whenever you have a standard curve. In the second standard deviation, or within two standard deviations of the mean, meaning two this way and two this way, 95% of your data is going to fall within two standard deviations. And lastly is three standard deviations, and 99.7% of the data are within three standard deviations of the mean. So when teachers or professors talk about grading on the curve, that's what this means. It means that no matter what, 68% of the class is going to fall within this average. So if the class would have an average score of 75, 75 would be here. They would figure out the standard deviation, and they would figure out how 68% of the people would fall within that standard deviation. So they would fall within one letter grade above and below that. So your standard or your mean would be like a 75%. And so even if, so let's say the test was out of 100 points and the mean ended up being a 90. This is how grading on the curve goes against you. If it's out of 100 points and the mean is a 90, I don't know why it's not working. Let's try again. But if your mean was a 90, and say your standard deviation was 2, then if you got a 90, you would have a 75%. If you had an 88, then you would fall down to within one standard deviation of the mean. So anyone with an 88 up to a 92 would fall within this range of one standard deviation, which would mean that that amount of people, this group would have a D, and this group would have a B. So even though you got a 92 on the test, you would only have a B. This group here would have an A. So that would be the people who got between a 92 and a 94 would have an A. If you got between an 86 and an 88, you would officially have a low D or an E. And then if you got between a 96 and 98 or higher, then you would have an A plus, and you would definitely have an E if you got an, would that be an 86 or lower than an 86. That's how grading on the curve can work against you. How it can work for you would be if this number was not a 90 in here, but the average out of 100 was, say, a 16, which I actually had in college once. Somebody got our average was a 16. And so with a 16 and a wide standard deviation, if you fell within this range, from a 16, I believe it was down to a 6, then you had a C in the class, or a C on the test. So 6 out of 100 got you a C on the test. It was a pretty hard class. I mean, I got a C, but I can't really brag about it. If you had between like a 16 and a 26%, then you got a B. At 26%, set the A's off. So anyone who got above a 26% had an A. All right. Now the bell curve is actually observed in nature fairly often. I'm going to pull this video up. So this video is about a thing called the Galton board. What the Galton board is, it's like a giant game of Plinko, where you drop a ball from the center and you see, and they're calculating or figuring out where it would fall. Okay? So anytime we drop a ball from the center, we can figure out that 68% of the data will fall between one standard deviation of the mean. On top of that, like we said before, it forms a standard curve where you would have 95% within two standard deviations of the mean. Now this is actually like math in action. And so this machine was set up just to figure out if it actually works, that we drop the balls from the center and see how they land. And so it's just consistently dropping them. You can actually see the standard curve being formed just from a natural process of dropping the balls. And this runs in repetition over and over again. Now, is it always going to be perfect? No. I mean, you can see it rises above in some of them. Like here, it's a little above. But generally, after running it over and over again, you'll see that it falls within the general standard curve based on the probability of where the balls are going to fall at. With this in mind, it makes me think about the game The Wall. Like, how do they come up with where they place the numbers? Based on how the balls are going to fall from each slot that they drop. It's an interesting concept to me. All right, we're going to finish these notes tomorrow. I clicked the button